Alright, so in terms of given variables, derive equations for the charge and current as functions of time. So in an RC circuit, which is when like a resistor R is in series with a capacitor C, RC circuit, there's going to be some current to begin with, but what you can imagine is over time, this capacitor is going to get fully charged up, and when it's fully charged up, it can't have any more current going through it. There's going to be no more current that's going to be, wait, I'm just repeating myself. Yeah, there's going to be no more current flowing through this circuit. Now, why, what to really think about why this happens is that, pretend, let's say we close this switch. At that instant, what's going to go on with our circuit? Well, let's say there's going to be, and remember, in a circuit, electrons are the ones flowing, but, convention, we're going to pretend it's positives that are flowing the other way. So we're going to have, let's say there's going to be one initial kind of positive charge, there's going to dq, whatever, and it's going to go through this little resistor, and then in this capacitor, initially, there's no charge on it. So what's going to happen is it's going to sit here, right? And then at that instant it sits there, a positive, right? Because there's going to be that, repulsive force. A positive right here is going to leave away. And what's going to happen? Well, you're going to be left with, so as this positive leaves away, and you're going to be left with a negative, right? Because if we think, let's say there's like, it's like equal, it has a certain, no charge or whatever. When you take one positive away, you're left with a net negative charge, and you have a positive going back, and this is a closed switch. And yeah, and just remember, really what's going on is we have negatives going the other way. So instead of a positive going to the plate, it's actually a negative going here, and then a negative leaves out there, and you're left with a positive. It's really just reverse of what I explained, but we just use this convention. Okay, cool. Now let's say another positive, or there's going to be more positives coming through, and as they start reaching this parallel plate, I don't know what I'm saying. I was trying to say capacitive plate or something like that. As more and more positives kind of show up, they're going to kind of encounter kind of a resistance almost, where it's like, oh shoot, there's all these positives, and they have their own like kind of repulsive forces. So less and less positives are going to end up on this plate. I mean, at least there's going to be less and less kind of current, because what's going to happen is eventually this is going to get fully filled up. You're going to have, and then obviously we're going to have the same amount of kind of negatives on the other side. That capacitor is going to get fully filled up. It's going to be at full capacity here, and there's no more positives. They don't have anywhere to go. It's like, oh, I can't stay here. Well, you get no more current. So that's just what's intuitively going on, right? So what we're going to do is we're going to kind of think about, okay, let's see at like a certain time, what is the charge on the capacitor, and at a certain time, what's the current going through this whole circuit. And that's what we're going to kind of go through today. And it's really just an application of Kirchhoff's laws and some calculus. So let's think about this. So before we have any charge, right? I'll just redraw this whole thing. Before you have any charge on anything, and t is equal to 0, what's going on? Well, we kind of talked about how the initial charge is going to be 0. I'll say Q naught is 0 coulombs. And what is the initial current? Well, the initial current, we can actually use Kirchhoff's law to figure that out. You can kind of have a guess as to what the initial current is going to be, based on what I was saying earlier. If we think about Kirchhoff's law, so the sum of all those voltages is going to equal 0. So we're going to have the EMF of the battery, and I kind of erased the variables, minus the current times R, right? So this is the voltage drop by that resistor, minus, well, the voltage drop of the kind of capacitor is going to be Q over C, right? And that just comes from C is equal to Q over V, and we're just rearranging those variables. hey, Q initial is 0. So at time 0, this whole term becomes 0. We know that this, because of Kirchhoff's law, the sum of all those voltages is 0. And we get that I is equal to EMF over R. And, I mean, that's just kind of Ohm's law, right? We know that current is equal to V over R, and we just kind of have an application of Ohm's law here. And this kind of reveals that at t equals 0, yeah, this just acts like a wire. It doesn't act like there's any kind of resistance or anything. You can just use V equals IR and pretend this capacitor doesn't even exist at time equals 0. So, the initial current is going to be EMF over R. So, current initial is going to equal EMF over R. Now, at a really long amount of time, we're going to treat it as kind of infinity. After a really long amount of time, we're going to talk about why the infinity stuff is coming up. After a really long time, that's just code word for infinity, what's the Q initial going to be? Well, in order to kind of figure that out, or Q final, sorry, what is the current final going to be? Well, we kind of talked about this after a really long time. When that capacitor is basically fully charged up, there's going to be no more current flowing through our little circuit thing going on here. So we're going to say 0 amps of current. Well then what's going to be Q final? Then we can kind of go back to our Kirchhoff's law. The sum of all the voltages is 0, which is going to equal the EMF minus the current times R, the voltage drop by that resistor, this just is Ohm's law, minus Q final over C. Alright, so, and I can just kind of get rid of that. So, the initial current's going to be, the final current's going to be 0, so you're left with EMF minus Q final over C. When you rearrange the variables, you get Q final, oh my god, Q final is going to equal EMF times C. Once again, this is just the definition of capacitance, right? C is equal to Q over V. And then if you multiply both sides by V, yeah, V is our EMF. So when at these kind of limits where t is equal to 0 and when t is equal to like basically infinity, you just kind of get like, it's like kind of a scenario we're actually pretty familiar with. When there is no, when there's only one resistor, is at kind of t equals 0. When there's only one capacitor and there's no current, you have this scenario. So this is kind of stuff we're familiar with. We can get started with the derivation now. So we're just going to use that Kirchhoff's law idea of saying that, okay, well, the sum of all the voltages is going to equal 0. What are all like kind of the voltages at play? Well, we have the EMF. We have the potential drop by the resistor, IR, and minus, well, what's going to be the voltage drop, or as voltage drop by the capacitor? It's going to equal Q over C, right? That's kind of the voltage the capacitor takes up, if you will, right? Some of the voltage goes to the resistor, some of it goes to the capacitor. The voltage taken up by the capacitor is Q over C, and we're going to have it all equal to 0. So, what you can do now is you gotta kind of have to realize that, hey, current is actually just really equal to, so current is just dq over dt, right? So EMF minus dq dt, right? The change in charge over your change in time times R minus Q over C is equal to 0. So now what we can do is we can kind of solve, kind of like we're going to basically do a differential equation. That's what I'm hinting at. We're going to do the separate, integrate, celebrate, whatever the heck that stuff is, that nonsense, that garbage. We're going to do it, and we're going to say, okay, we're going to get our dq dt on one side. So EMF minus Q over C, just for simplicity, we're going to kind of make this one fraction. So if we want to do that, we got to multiply a C here over C. And then you get C times epsilon minus Q over C. Okay, so then we have equal to dq dt over R, or times R, and then just to get everything on one side, we'll divide by R. So we get something like this. And then we're going to do the integrate, separate, I always try to separate, integrate, celebrate. So we're going to get all our DTs on one side and all of our DQs, or all the Q stuff on one. So I want Q on this side, so I'm going to divide by C times epsilon minus Q, and I'm going to multiply by DT. And I'm going to do that on both sides. Right? So I guess I'll do something like this. So you're gonna get dt over RC equals dq over C epsilon minus Q. Okay, so I'm gonna want to integrate, but before I do that, you have this, ideally, you on your calculus equation sheet, we know that the integral of 1 over x plus a is going to equal, or dx, right? dx over x plus a is equal to ln x plus a. So I want this in kind of an x plus a form. Right now we have like an a minus x. So I'm going to multiply both sides by -1. And what that does for me, if I take this -1 here, it's going to make this positive and this negative, and then it'll just make this side negative. So I just get dt over negative RC is equal to dq q minus C, or C epsilon. Okay, now I can integrate. So I'm going to actually just bring this over, and I'm just going to check the time. I just want to make sure I'm not wasting too much time. Okay, 11 minutes. So we have dt over negative RC is going to equal dq over q minus C epsilon, and then we're going to integrate. Now, what are our bounds going to look like? Well, I guess this is pretty. I guess this one's pretty simple, right? Because for dt over negative RC, we're going from 0 to t. We're trying to figure out what is the charge. Well, like we're taking the integral from time 0 all the way to the time t, where we want to figure out our charge at that time, right? So this is kind of the function of time part. Let me word that better. It's like we want to find the charge at a certain time t. So I'm going to do my bound from 0 to t, right? Because that's the t that I want to find the charge at. And then similarly, the initial charge is 0. And then at time t, whatever that time t is, I'm going to have a certain charge q, which is kind of what I'm solving for. Q is a function of time. So those are going to be my bounds. This is pretty simple, right? So if you were to integrate this, you get t, negative t over RC. And the reason is because you can pull this out of the integral. You integrate dt to time t, you get you get t. And then for this integral, we're gonna have ln. So we're gonna have basically ln q minus C epsilon minus ln, and we're not just gonna leave it like this, right? We have, for our bounds, we're just plugging in q here and then 0 here. When you plug in 0 here, or sorry, when you plug in 0 for C or q, you get just negative epsilon C. So, okay, and then we can use our properties of logarithmic stuff and say C cubed minus C epsilon over negative C. I need to be consistent if I'm doing C epsilon or epsilon C. My fault. Alright, and then we're just solving for Q kind of as a function of time. So we're going to say E, right, to get rid of that ln. So we have E to the negative T over RC is equal to, that kind of cancels out. You get Q minus C epsilon over negative C epsilon. And then you just kind of solve for C. So I'm going to multiply both sides by this, and I'm going to add the C epsilon. So I get negative, and I'm going to actually do epsilon C. I wonder why. I'm going to change it to epsilon C instead of C epsilon, even though they're algebraically the same. Negative T over RC is going to equal Q minus C epsilon, or epsilon C, for EMF, by the way. Not the other thing, but you probably caught that by now. I'm going to kneel down here. Epsilon C minus epsilon C e to the negative t over rc is equal to q. And then we factor out the epsilon c. You get 1 minus e to the negative t over rc is going to equal q. All right. That is going to be our charge as a function of time. And let's just see if this kind of is consistent with everything we've been kind of doing. Like let's check our bounds kind of. At t equals 0, when you plug in a 0 here, you get 0 over r2, which is 0. So you have 1 minus e to the 0. E to the 0 is 1, so you have 1 minus 1. That's 0, and that 1 minus 1 becomes 0. Multiply by this, doesn't make a difference. Your charge is 0. Now, what happens when our t is infinity? Well, e to the infinity is going to be a really big number. And negative infinity is just 1 over e to infinity, right? So if I'm doing this, that's the same as this. So that's going to be a really small number, 0 basically. So you have 1 minus 0, which is going to equal 1, times epsilon naught c. Your final charge at t equals infinity is going to equal epsilon naught times c. Okay, let's quickly find current as a function of time. How are we going to do that? I don't want to do all this again. Guess what? You don't have to. We know that current is equal to dq over dt. Let's just take the derivative of this as a function, or with respect to time. So if I were to just really quickly do that, so I would have current as a function of time is going to equal d over dt, that whole function we just derived. So epsilon naught c 1 times 1 minus e, oh my god, times t to the rc. Okay. So, oh, and there's a minus right there. If we're differentiating anything, e epsilon naught times c, you can just pull that out. It doesn't depend on time. Okay, and then we're going to differentiate this 1 minus e to the negative t over rc. The 1 doesn't make a difference. It's a constant, so it's really just the same as taking the derivative of this. So to take the derivative of that, we're going to have to do kind of a chain rule thing. So d outer is going to equal, I'll do parentheses, I guess. D outer is just e with respect to this stuff, so you just end up getting negative e to the negative t over rc. And that just comes from, e to the x is a derivative of e to the x, and watch calculus videos if what I did just made no sense right there. And then we're gonna just multiply it by d inner with respect to time, so that's negative, so that's the same as just negative t, or negative 1 over rc, right? So these negatives drop because we're canceling, and we get current as a function of time is equal to it's equal to, what is it equal to? Wait, EMF times C, 1 over RC times e to the negative t over RC. Oh my god, these RCs. But guess what? When you multiply EMF times C over 1 over RC, those C's drop, right? So you're just left with I of t is equal to EMF over R times e to the negative t over RC. Let's just quickly check our bounds. When you make t equal to 0, you get e to the 0th power, which is 1. So it's just 1 times EMF over R. Yeah, the current at time 0 is just EMF over R. That's what we realized. And then the current, when t is equal to infinity, e to the negative infinity, we just talked about it, is equal to 0. So 0 times anything is 0. Your current's going to be 0 at t equals infinity. All right, so that's what I'm going to leave you off with. But one thing I want you to think about, let's say the final current we talked about is going to be this EMF times C, right? When t is equal to RC, right? So if you were to take R times C, and then that's your time, what fraction of the final current is going to equal the current at that time. I want you to think about that. I wonder if that'll be of any importance ever. And yeah, thank you for watching.